did the conservation of angular momentum. We did this. Torque is dl dt, the rate of change of angular momentum. Then we said when the torque external is 0, then the angular momentum is constant. Angular momentum is conserved. Just like force is equal to dp dt in linear momentum, and when the force external is 0, so if two blocks hit each other and the force external is 0, then the linear momentum is conserved. So the next example we did was something that's spinning. Okay, it was like a problem we got off the internet. It was a wheel that was spinning, and then there was a cockroach walking backward, right? And then they gave us the spin rate, and then it said the cockroach stopped. So by stopping, what did he do? He pushed off the table, and then the table started spinning faster. So then we calculated by doing conservation of angular momentum, I initial, omega initial, I final, omega final. So this problem was a good use of angular momentum conservation and the equation, because when the roach is walking, he's walking at a different velocity than he's not just a part of the spinning disk. He's walking with respect to the disk. So you have to do here the moment of inertia of the disk, omega of the disk, which is into the board, right? Then you have to subtract his angular momentum, which is RMV. So RMV, which is out of the board, right? RMV. And then once he stops, he's spinning with the disk. So his moment of inertia gets added to the disk's moment of inertia. So then we're gonna have here the moment of inertia of the disk, M disk, radius of disk squared, plus the moment of inertia of the cockroach, which is RMD squared. So then the ID is gonna be half mass of disk, R of D squared, omega D. So that's the moment of inertia of the disk times the original omega of the disk minus the rate of walk of the cockroach, RMV, the velocity of the cockroach, and then divided by the total moment of inertia. Okay, so this is one of the kinds of examples where angular momentum conservation is involved. We could do another one, like, for example, this one is a good example. You could have a disk like this, and there could be a hole, and there could be an object here hanging, M, and then it could be another object here. We could make this big M, let's say 10 kilograms. And then there could be a light object here, let's say 2 kilograms. And then this is going around the circle, like that. Okay? So let's say you have something hanging, and then you give the 2 kilogram object, it's sitting on a frictionless disk. So then you give it a certain kick so that it goes around with a certain velocity. So what velocity should you give so that it goes around without the radius changing? So it goes around in stable circular motion. So that's the first thing we can ask. What should V be so that the 2 kilogram object maintains uniform circular motion? And then maybe the radius can be given here, let's say 1 meter. the radius of the string, this string doesn't matter, the hanging string. It could be as long as it wants. So that's the first thing we can ask, and then we can make that a bigger problem by adding some more components. So here we have tension in the string, and we have the weight of the object, 10 times 9.8. So that's 98 newtons. So the tension in the string, by virtue of the hanging mass, is going to be 98 newtons, right? Tension 98. Then that tension is going to propagate all the way to the top, and it's going to pull in on the 2 kilogram object, right? It's the same tension. So then you're going to have T is going to equal little m v squared over r, right? So the tension T is 98. M is going to be 2 v squared over r is going to be 1.
Is the tension the force?
Is the force provided on this object by the weight of this,
Okay.
by virtue of the hanging mass. But the velocity is provided by you. Someone has to give it the kick so that it goes around. So same thing with the planet Earth. Who gives the velocity Earth the velocity that it needs to start going around the sun? It's not the sun, because the sun would just like to pull us straight toward it, right? So it's the original nebula from which the solar system forms, right? The nebula collapses. The nebula collapses and starts spinning. So when a solar system forms, it forms from a spinning nebulae. So it's the angular momentum conservation that occurs when a nebulae starts spinning and then goes like this. So then what happens, certain planets in certain locations will start coalescing in the right location and happen to have the correct velocity at that location.
They talked about this at the Caltech thing on the stargazing. That's a big thing in star formation.
Exactly.
The fragmentation.
The fragmentation
Yeah.
of planets.
Yeah.
So it could be that you form a planet and maybe it doesn't have the right velocity. It's going too slow or too fast. So it might be flung out, right? And it might be gone to another solar system, might steal it away from us, right? So that's what we're doing, is we're saying at this radius, what does V need to be so that it maintains that radius, right? And then that's what V needs to be. So then you're going to have 49 is equal to V squared. V is going to be square root of 49. Oh, happens to be a perfect number. Perfect, the whole number, right? 7 meters per second is what velocity I need to give it. So now we can add another component to that problem. Let's say you've given it that speed, and without friction, it can potentially go forever, right? If there's no friction, just goes spins forever. It's almost like those superconducting pucks. Then you spill liquid nitrogen or something, and then it starts going, becomes a resistance of 0, right? Then we can add, what if we add another 10 kilograms to the hanging weight? So now we can ask, what's going to be the new radius? So it's almost like asking, what if the sun all of a sudden doubled its mass right now as we're going around the sun, right? What would happen, right? So what if we add another 10 kilogram to the hanging weight? What is the new radius? And new velocity. So what if the mass doubled its size? Would we start spiraling into the sun? Or would we start spiraling away from the sun and settle at a farther orbit?
I think the radius would get smaller, right? We get closer to the sun.
Why?
Because it's got a heavier weight, pushing, dragging it
Because
down on that.
just like with that string, isn't it pulling inward more?
Okay.
Wouldn't that be the sun?
Yeah, so that is playing the same role as the sun, yeah.
So if that's heavier, it's going to pull it in more, right?
Okay, so the same logic that works here should work with the sun.
Yeah.
Even though it's not a string,
Right.
right? If the sun were to double its size,
Gravity's like
And
an invisible
then,
string.
so then maybe we're gonna start spiraling into the sun, and then settle in a new orbit.
So speed for the unchanged,
The speed remain unchanged?
Huh.
but because like for the simulation it can be like different
Well, there
range
has to
for
be a
different
change in speed, doesn't it?
Yeah, in other words, what changes here? Just the radius changes, or does the velocity also change?
Yes,
The velocity
but
has
if we
changed too,
don't have
right?
two changes, so
Because the radius is different, doesn't mean it's gotta go, well,
That's a good question.
Yeah.
Is did I ever give you guys the example of that ice skater problem that I missed on the scholarship test?
oh yeah,
Yeah.
you did.
Oh yeah. Then I said that problem, but it was a while ago. It wasn't. I should have given it during this chapter.
Well, it's because you said, I think it was for the
When was it?
final velocity was the same even though.
Yeah.
And then.
Which chapter was it that I gave that example? When I.
Oh, we were
about
studying
cross products?
tangential
Like,
velocity,
for the
I think.
angle?
I don't.
is that for the angle or
I forgot when it was, but
Yeah.
anyway, it was something like this.
Oh, it's the third test.
Like a post and then a chain on the ice. And then I said, oh, okay, so you have an ice skater that comes with a velocity, picks up the chain and goes like this, like this, like this, until their radius is half the radius, and then they let go, right? So what's the final velocity? So in my answer, I told the committee the final velocity is 2v.
Right.
Because what I said was angular momentum is conserved, right? So if angular momentum is conserved, mv1 r1 is mv2 r2. So if v2 is half of v1, r2, if r2 is half of r1,
Then it should be two.
then v2 should be double v1. That's the argument I made.
Right.
But the other thing that could be conserved is kinetic energy.
Oh.
Right, so the other culprit is kinetic. If kinetic energy is conserved, then V1 equals V2. Well, if this is conserved, then if V1 is V2, then angular momentum is lost. So, well, which one is this? Is this a case of angular momentum conservation or kinetic energy? And then which one is this one? So I didn't think about it too deeply, so I just said, oh, it's a case of angular momentum conservation, and the velocity, therefore, is gained, right? If the velocity is gained, some force is doing work on the system, right? So it's a matter of a battle between work, which is R crossed into F. Sorry, not work is R R dotted into F,
Yeah.
where R is the distance that you're going, and then dotted into the force, right? So it's a matter of, is the work zero or is the torque zero? Torque is R crossed into F. So then when you analyze this more detail, you really notice that the work is zero, but there is a torque. Let's see. So, so where's the R measured from? The R is from the center of the post, because that's where you're going around, right? You're going around the center of the post. So this is the R from here to where you're holding the chain, and then the force that the chain is exerting on you is this way. So as you're spiraling, no matter where you are, the chain is kind of starting to wrap around. Chain goes like this, and then R is like that, F is like that. So R crossed into F, right? R crossed into F, it's into the board. So it's an into the board torque, but your angular momentum is which direction? R crossed into P, right? R crossed into P out of the board. You see? So your angular momentum is out of the board, and then your torque is into the board. Into the board is an X. R cross into F, right? So what's gonna happen? If the torque is into the board, the angular momentum is out of the board, the angular momentum is gonna decrease. So if it's gonna decrease, what's gonna happen? it's possible that L2 is less than L1. So from there, all you can determine is that it's possible that this is less than this. I mean, not it's possible, it will be less, right? L2 is less than L1. But you still can't argue that V2 is the same as V1. Then you have to go over to work. Then you have to say, okay, an incremental, let R be a dr, so that's an incremental, it's much different than this R, right? This R is an incremental tangent to the path that you're taking, right? It's a vector tangential to the path. And then F is the vector the chain is exerting on you, right? So what's the work done? Oh, perpendicular. The work is 0, right? And when the chain is here, what's the path you're taking? dr like that. And then the F is also like this. Do you see?
Right.
So as you're spiraling inward, the chain is always making a perpendicular angle to the edge of the post, the edge of the pole, around which you're turning, you see, as you're spiraling inward. So that the R and the F are always perpendicular. See, your path looks like this. And then this is the chain. Right? And then the R looks like this. dr, we can call it. And then the F looks like this. Well, if it's perpendicular, no work is done. Then you can say, well, if no work is done, the V2 is the same as V1. Then if the V2 is the same as V1, then that means the angular momentum is exactly halved by the time you get to half the radius. You see? So V2's got to be equal to V1. Therefore, R2 equals half R1. So the angular momentum 2 is half the original angular momentum. Right? So that means the torque is equal to delta L over delta T. The loss of momentum is going to be L2 minus L1 over the time that it takes. And then the torque is going to be this R times F times the angle between them. Is that angle going to stay the same? R, F, sine of that. Yeah, it's going to stay the same, yeah. R, F, sine of that angle, which is going to be the radius of the post divided by, you could even do more detailed calculations. Should I give that on the final?
Why is it that L1 is greater than L2?
Because the radius is
Well,
decreasing.
just from torque, we
Oh.
determined that it's already could be less, but from the work, we definitely know it's less,
So,
because V stays the same.
but if the radius was equal the whole time, like if that was like a pivot, like it swiveled, would they both be conserved? Linear,
If a post was very short, like very small,
Or-
yeah, he would just keep going
and
and just end up the same place.
but I mean the velocity, the final velocity would still be equal to the initial.
Yeah,
So it's like softball players when they throw a ball and they rotate their arm all the way back.
it's different, yeah, not quite like that.
Okay.
This is more like the, I'm thinking like a tether ball, and you hit the tether ball as it goes around. But in that case, the velocity gets faster, right?
Yeah.
I used to play a lot of tether ball when I was a
Not
kid.
like the
I
baseball,
love that game.
but you know like the
Yeah.
women's softball, where they like,
That one goes like this and starts wrapping around, but the velocity increases, right?
Why?
Yeah.
That's why you have to hit it the other direction as it's.
Oh yeah.
Yeah.
I see what
But
you're
in this case, the velocity is not increasing.
Uh-huh.
It's actually staying the same. Yeah, staying the same.
Why?
So then why did the softball players, like the ones that they throw it underhand and they rotate their arm all the way around and then they release it from...
That's just more conservation of energy. Potential energy converts into kinetic.
Okay.
It's not like no.
Yeah, I just always...
Yeah,
when
no
someone
torque.
asked me about that, I was talking about physics, I go, I'll come back to you on that.
I mean, maybe your shoulder is applying a torque. Yeah, yeah, kind
Yeah,
of.
because they do a full circle and they release it from the bottom.
I'm just thinking that's just more potential energy and then kinetic energy
Oh, that makes a lot more sense.
converts into kinetic.
Oh, okay.
Yeah.
Forgot about the potential energy.
Let's see, the tether bolt is like this. You hit it, goes, wraps around. Chain is like this. Tension. On the tether ball, there's a little hook that it's on, right? It's hanging from a hook. So as the thing goes around, this is a more complicated version of this because it's three-dimensional. You have to visualize, is there a torque on the thing? In this case, there is a torque, but there's no work. So here, is there work being done by the tension or not? This one is going like this. Tension T.
I don't think so.
So I don't think it stays perpendicular throughout the whole. Or
But
does
then
it?
because of gravity, it starts to go down, right?
Yeah.
Because you first go like this, you hit it, it goes around, but then as it's going around, it starts coming down, right? Doesn't it? It starts wrapping around down. The motion of that is pretty complicated. But I note in that case, the velocity does increase. Because of gravity. Oh, you know what? Maybe gravity is doing work on the system. That's why it's speeding. Yeah. Because here, this is only the tension. The tension is not doing any work. Ah, yeah. Because the gravity is this way, right? mg. So if we did mg, and then its path is like this, like it starts up here, and it goes like this, and then it starts dropping, right? It's almost like a helix, like this.
Mm-hmm.
Then you have to hit it here before it closes, it ends, right? So as you go like that, is there work being done? Yeah, gravity is like this,
Oh, it's
and
going,
then this is
yeah.
the tangent. There's the angle
there's
is
a
not
down-
90.
Yeah,
Gravity is
it's
doing
getting
work.
lower.
So the velocity is increasing, and also the angular momentum is changing. You know, so angular momentum is, so there, in that case, there's a torque and there is a work.
Right.
Pretty complex physics there.
Because it's going down
Oh,
and
in that
inward.
one. Oh, you mentioned that.
This is
before.
the
Yeah,
this is
yeah.
the tether ball. This more complicated version. Do you guys do that in your country? You play tether
Yeah.
ball when you're
Yeah.
kids? The playground?
Yeah, they,
Yeah.
You guys do that in, I don't know, in Hispanic countries? Do you play that? Anyone from Mexico or? Do they play that? One of my best favorite. You don't know what that is?
yeah.
Do they play that in other countries?
They
Or is
play,
it just an American game? Do they play that in China?
No.
You know which one
I
I'm saying?
can't-
This one.
Yeah.
Maybe you
I
guys
guess
don't
we
know.
could just Google, do they play tetherball in Mexico?
It's so strategy. That's where I learned how to do physics. From there, I decided to become physicist.
Well, I know like boxers, they have a ball that's on 2 elastic ropes and they punch it back and forth.
Okay, so you see, you do it a little bit higher because you know gravity is going to bring it down. These guys aren't real pros. I was tough at that. Oh, you see how it's wrapping up and speeding.
Yeah.
Yeah.
Because of
And you do it kind of high so the other person can't reach. You see that?
Oh. Like, I feel like we had.
We should have one here at ELAC.
I feel like we had these in school, but no one really taught us the rules. We just.
Oh, this is fun. Yeah,
I
real
remember
fun.
them, but I don't feel
very
like
competitive.
I don't feel like they ever like sat us down.
They
and
should
told
have
us
like
how
a
to use
world.
it.
They should be part of the Olympics.
Like, I didn't even know there were rules.
Oh yeah.
Like, how,
Well,
how
I
do you
guess
get a
you
point?
could make it more official, make it a point system, and how do you score points in this? I guess when the ball finally just
This is-
wraps completely around.
This would be good training for like volleyball, I guess.
It is a good, yeah.
Yeah. Like,
But
they
you see,
taught
the
us-
physics of that is complex. You've got rotation around the post,
Right.
then you've got gravity doing work as it's spiraling down.
Yeah,
You
right.
see?
and angular.
And in this case, angular momentum doesn't conserve.
No, angular momentum doesn't conserve, and work velocity is not the same either. Kinetic energy is not
Because the
conserved.
radius and the force is not, it's not in the same direction.
Exactly.
Yeah.
Yeah. So in this case, work is 0, but torque is not 0. This one, it's going to end up that torque is 0. Wait. Yeah, torque is 0, but work is not 0. Okay? Opposite. So why is that? Well, you see the hole is so small, and it's just like a hole. So from a top view, this is what it looks like. This is the hole. So then you got like this, right? And then you got the object is like this, and then it's gonna start spiraling in, right, when I add weight. So then when you spiral in, it's gonna look like this, delta R. And this is the F. Well, you can already tell that it's not 90.
Yeah.
Here it is 90 because delta R, it goes like this around the chain, the edge of the chain, right? And the chain starts wrapping delta R. Ooh, very tricky there. Here, you go like this and then starts wrapping, wrapping, wrapping. So here's delta R. Here is F. So the direction of the F is never changing, right? It's always towards that hole. And then delta R, let's see here, as it goes like this, so delta R, delta R, delta R, delta R,
I see.
and this is F. See, that angle is less than 90. So there's definitely work being done in accelerating it. It's getting faster. But how about the torque? Torque is going to be R crossed into F. See, what did we do for the R here? For that one, the R means the vector from the pivot point. So you're going around the center of the post, right? And then the F is to the edge of the post.
Oh, that's
You
what
see, that's
changes
different.
everything.
But here you're going around the center of the center, it's just a hole. So this is the R. And then the F is also towards that center. Anti-parallel. What's the cross product? R cross into F? Zero. Very tricky, slight nuance, right?
Yeah.
So here the torque is 0. That means this is classic angular momentum conservation. You see?
That is tricky.
So this is more similar to what would happen when the star gains mass. If it gains
Yes,
mass, you would start spiraling into the planet and your velocity would increase.
Yeah.
And the planet will do, gravity will do positive work on you, right? So, so then we know now that the angular momentum is conserved, mv1r1, mv2 r2. But that only tells us that the product of V1 and R1 is V2 to R2, but we don't know what they are, because we don't even know what R2 is. So now we need to use the other equation. The tension is what? It doubles, right? 196. The tension doubles, so then we're gonna say 196 is equal to what? mv squared over r, right? mv2 squared over r2. So remember the first tension was 98, right? So then we're gonna say the mass is what, 2 kilograms? So 2 goes into that, becomes 98 again. So this is given by the centripetal force equation, which puts a condition on what V2 and R2 need to be, right? This is from the F centripetal is mv squared over r. This one is from the angular momentum conservation, which puts a condition on what the angular momentum needs to be, right? So together you should be able to solve them. So then you can say R2 is going to equal what? V1 R1 over V2. And you can put that into this R2. 98 is equal to V2 squared over V1 R1 over V2. Then take this to the top and cross multiply. 98 V1 R1 is equal to V2 cubed. So it became not as easy as you would think it was. It's not just V1, V2 is V2. It's not a simple ratio, because you have to do this, then you have to apply force centripetal equation. Then you're gonna have here what? 98 V1. Well, V1 we already knew, right? What was it? Oh, that was the initial velocity, 7. R1 was the original distance, 1. V2 cubed. Okay, then that's going to be the final velocity. .819. So what was the original velocity? 7 meters per second, right?
How are you gonna explain the angles between the velocity and then the radius is 90 degrees?
Eventually, when it settles down and becomes a stable orbit, then it's going to be 90, back to 90.
It's always 90 in this motion?
No, as it's spiraling, it's not 90. What did you say? What angle between the radius and this thing?
Yeah.
Yeah, see, it's not 90
It's not 90.
because it's spiraling inward.
Oh,
MVR.
so that's how you determine a stable.
Because if it
unstable
was
orbit.
90, there would be no work. Hold on.
Yeah, no work.
Yeah, no work done. In this case, there is work done.
There's work on that.
The gravity is doing work. In other words, it's like the tether ball example. As the tether ball is going down, gravity is doing work, right?
And my question is, since angular momentum conserved, so mv1r1 is equal to mv2r2, but isn't that defined as mv1 cross product into?
Oh, that one is it is 90. It's the hold on. No, that one is not 90. It's R
Yeah.
crossed into
V.
V.
So that's 90. Or not? Because if it's not 90, why don't you put like sine theta?
Yeah. Very good question. He's saying, why aren't you putting here? You're trying to say what,
Yeah,
we need to
there's
put an
an
angle
angle.
maybe there?
Yeah, unless it's 90 degrees.
Oh, you know why? Because this is the original stable orbit velocity. That's the final stable orbit. But in between, the physics of that is
complicated.
complex.
So
It's a spiraling orbit. So I don't care about the velocity during the spiral,
Good.
you know? It's more complex.
Yeah, so it doesn't really matter like how it goes, but it just matters like the beginning and then
And then at the end.
at the end.
But the spiraling, it's there is an angle other than 90. That's
right.
true. Yeah.
Okay,
Yeah.
makes more sense.
So in planetary orbit, how does something go from being unstable to just
Well, this one I'm assuming you double the mass of the sun. Let's
Right.
say.
no? But like, let's say something enters our solar system, starts orbiting the sun. How does it go from being unstable to?
Well, you need to change something about the system. Either the sun has to lose quite a bit of mass, or it needs to gain mass.
Or else it would just
But
eventually
we
spiral
do know
into
from stellar evolution that eventually the sun is gonna get large,
Yeah.
become a red giant,
Right.
right? It's gonna burn up the earth. But let's just say it doesn't burn up the earth. Forget that a second. Let's just say it becomes a red giant and the earth is fine and dandy, right? Then after the red giant stage, the sun is gonna release most of its masses.
Yeah.
It's gonna get much lighter. If the earth is not burned up, what's gonna happen? The opposite of this, it's gonna go like from 10 to 1 kilogram, let's say.
Ah,
The sun will turn into a white dwarf star.
yeah.
So what will happen to the earth? It will spiral outwards.
It's funny because in the
Just like this problem, we can say if the mass goes from 10 to 1, what's the new velocity? Well, we could do a calculation, figure out the new velocity.
it's funny because in the stargazing thing, they said that they're not sure why, but I think our sun's evolution is like 100 times slower than most of the stars they observe, and they're trying to determine that with computer modeling.
Nice.
So that's why we're very lucky.
Did you guys go out and do observation? Because that's the
No.
reason I canceled it. It was overcast.
So I think it was me, and I think his name's Andrew, right?
Yeah?
Yeah. So we went and we sat through the lecture series, but then they told us that there were no
Because
stargazing.
they said
but
originally half an hour was the lecture,
Yeah.
and then you go out and
Yeah.
do, so they just did a longer lecture?
Yeah, basically with a Q&A and
Oh, okay, well, that's still valuable.
yeah, it was good.
Okay, so then what happens to the R2? So then the R2, we can say, put in the original velocity, the original R, and the original, the final velocity, and that gives you the R2. Point 794. 0.794 meters. We could almost generalize that. We can say, this is such a general result that we can say any star that doubles its size, doubles its mass more, the planet going around it, the radius will go from whatever it was to 79% of where it is. You see? 79% of its location. And then the velocity will go from whatever it is to the ratio of that. It could be a very general result. So if you go to the Earth's orbit, the average speed of the Earth is about 30 kilometers per second, you see. The speed at aphelion and perihelion. So if you averaged it's about 30 kilometers per second. And then the distance of the Earth is 1 AU. So if the sun were to double in size, the distance would end up becoming 0.794 AU. Right? And then the velocity will become 30 times the ratio of 8.819 to 7. Oh. Nope. I'm wrong. This is, you cannot apply this to gravity. You cannot apply it to gravity. You know why? Because here, when I double the weight, this thing goes down, this thing goes in, the tension in the string remains the same. With a planet, if it goes into the sun, the force of gravity increases.
Yeah.
Ooh, so it's not quite the same, yeah.
Right.
The idea is similar, but
But
it's
still, like,
not the
Not
same.
exact number.
Yeah.
but-
In our case, the force is unaffected by its distance to the center.
yes.
Yeah. So that's a more physics 2 question, right?
Angular
Yeah.
momentum stays the same. I mean,
Yeah, the angular momentum still stays the same. Yeah, that one still is true. Okay, so now you see you know how to do this. What is the new radius and new velocity? That's a good angular momentum thing. So besides these two examples, the one with the cylinder and the adding weight, what other kinds of angular momentum conservation problems are there? Well, there's a whole host of them. There is a totally inelastic collision, totally inelastic angular momentum collision. So in chapter 9, what was the totally inelastic collision? What did it mean?
So,
Block hits a block
go together.
and go together.
Yeah.
So in this case, it would also be something similar, like a ball, very small ball, let's say, goes 2-kilogram ball, 3 meters per second, and goes and let's say, okay, you know that, let's take that bat that we did earlier. Remember the bat, the non-uniform density?
Uh-huh.
Looked like a sperm whale. And then, so let's say the bat is well, let's say the bat is just lying on the table, right? So the bat is lying on the table, and then the ball comes, hits the bat, and sticks to it. Instead of a ball, it could be, let's say, like a piece of gum or whatever. Comes and sticks. And together they start rotating on the table. Or this could be in outer space too.
Yeah.
You could come and hit something, attach, and then together they start rotating. Right? So then we can say, find omega final and B center of mass and percent loss of kinetic energy in this collision.
How much do we know about the bat?
Okay, so the bat, let's do the same exact bat that we did before in chapter 9, where we found the center of mass of the bat, right? What was the density? Alpha x to the third, was it? We found its moment of inertia, and we found its center of mass. What was the length of the bat? First, give me that. 4 meters.
Yeah, 4 meters.
Okay, and then the center of mass was 3.2 meters.
In the x direction.
Yes, of course, yeah, in the x direction, 3.2. And then, what else?
So mass of that was 10 kilogram.
Okay, mass was 10 kilogram. Did we find the moment of inertia about the left end? Left end,
Yeah, we did. We had 106.667.
106.667. And then did we shift that to the center of mass?
Yeah.
If not, we can do that one now easily.
So center of mass.
That was 4.266.
How would we do that? Even if we didn't do it, 106.667 minus what?
MD squared.
10 times 3.2 squared, right?
Mm-hmm.
Yeah. Did we do it?
Yeah.
Yeah.
4 point?
4.266.
Okay, so now let's say this ball comes and hits it exactly at its middle. 2 kilogram ball, 3 meters per second, comes, hits it in the middle, and sticks to it. Okay, so now,
If you hit that middle, will it rotate? Oh, because it's not a center.
oh yeah, the center of mass is off the center. Yeah, exactly. Yeah, center of mass is here.
Right.
So now what's going to happen? When it hits it, becomes part of the bat system, right? Kind of like the cockroach, right?
Yeah.
It comes to stop, it becomes part of a bat system,
And
it
changes
shifts the center of mass now. Because since it becomes a part of the bat, so we have to find the new center of mass. New center of mass, right? So how would we do that? Let's see here. Y center of mass is y1 m1 plus y2 m2 over m1 plus m2. So where should I put my coordinate? A good place to put it is right in the middle. X, Y axis. Right? So this is the original center of mass of just the bat, y1, right? So now I can do y1 is the center of mass of the bat, which is going to be what? 3.2 minus 2, right? Because I'm measuring from the middle. So that'll be 1.2 is y1. M1 is going to be the mass of the bat,
Bless you.
which was 10 kilograms. Plus y2 is going to be what? Well, y2 is actually going to be 0 because the ball is hitting the bat at its center and my axis is at the center, you see. So in this case, y2 is 0. y1 was 1.2 because it's this guy. 1.2 is from here to here. So the y2 is 0, then divided by the total mass of the system, which is 2 plus 10. So that tells me the new center of mass of the system. Okay.
Or in this case, that's non-uniform.
Well, the non-uniform we already know because that's how we calculated the center of mass.
Oh,
Yeah.
You know, we did the integral already.
okay, so we don't have to do it again.
Yeah. So that's the kind of problem you might see on the final. Like one problem says find the center of mass, do all that. Then the next problem builds on that. So if you did that one wrong,
Well, no, but
everything else is wrong.
what he's saying is, it doesn't just add to the mass of the bat, it adds the mass of the bat on one side. So when that
It
changes,
redistributes the center of mass so that it shifts it a bit.
yeah, but I mean, he's saying like, can we just use that simple equation to do that? Because isn't there gonna be more mass concentrated on a
Oh,
different
this
spot?
one takes into account whenever you have a bunch of objects that are glued together, this will tell
Oh,
you
yeah,
the
okay, so
center of mass
we're
of the
still
system.
viewing it as separate objects, even though.
Yeah, we are viewing it as separate
Ah,
objects to
okay.
find the new
Then,
center
yeah,
of mass
then-
of the system.
Yeah, I was just saying if they became one object, then the densities changes.
Yeah.
I see what you're saying now. Okay.
Okay, so then divided by 12, oh, then it just became 1 meter. So now the center of mass is 1 meter from the middle. It reshifted it, right? So now I'm gonna say the angular momentum of the system is conserved. Because this one hits this one. If there's no friction on the surface, there's nothing to provide a torque. They're free to rotate.
Right, around the center of mass.
You see.
The
So,
new center of mass.
so now they're free to rotate around what? Around the new center of mass. So the final angular momentum about the new center of mass has to equal to the initial angular momentum around that new center of mass. The funny thing is, before the event even happened, that center of mass didn't exist,
Right.
right? It wasn't like there was a center of mass there. But because that became the final center of mass, the angular momentum that you do has to be the initial, has to also be about that center of mass. You can't change your reference point.
So, I mean, it did exist because there's a point on the bat. It just-
Yeah, but
it
it's just
didn't-
that the
it
concept of it being a center
Yeah.
of mass didn't exist.
It didn't matter before.
Yeah, exactly.
And now it matters.
Yeah.
So I'll get it.
That's exactly what I want. Your enthusiasm and learning.
Yeah. That makes sense.
You caught on.
Yeah. Been studying.
So now you got here, this is what? L final, so the final moment of inertia times the final omega. So let's do the left side of this first. What's the final moment of inertia? So then it's the final moment of inertia of the bat with respect to that new center of mass. So then what is that going to be? Well, we found the moment of inertia around its true center of mass, 4.22, right? But then what do we have to do to that? If I want to find the moment of inertia of the bat with respect to that new center of mass,
We shift it.
you shift from here to that new center of mass. This way, right?
Right.
So plus nd squared, right? So 4.266 plus what's the mass of the bat? 10 times what's the shift amount? The center of mass is 1, right? From here to here. From here to here is 0.2. So it's barely a shift, but it is a shift, right? So it's a shift at 0.2. So you do 4.266 plus 10 times 0.2 squared. That gives you the final moment of inertia of the bat with the new center of mass, right? But the ball itself also has moment of inertia with respect to that center of mass. Just like the cockroach had moment of inertia with respect to the center of the disk, right? So then we have to add to that the moment of inertia of the ball.
Oh yeah.
Of the ball with respect to that new center of mass. So then that's going to be the mass of the ball times its distance from that new center of mass squared, which is going to be 1. Okay, see if you're understanding that, each piece of that. Review it in your mind.
So shifting. Okay. So essentially we have the original center mass, and then we have the moment of inertia, both the bat shift and the ball shift around the new center of mass. And we have to add that to the original center of mass, because that's where it would naturally be rotating before the shifts of the collision.
I like that, yeah.
How
Makes a
you-
long sentence, yeah, you're right.
How you say like torque is 0 in this case? Because the force and then the radius?
Because the only force on the system is their mutual force. The ball hits the bat hits the ball. There's nothing else that is exerting a torque.
Okay.
There's no friction on the surface. Or maybe it's in the middle of the air, and then something hits something,
Oh,
you
okay.
know,
Yeah.
and then it starts rotating.
Okay, so it's similar to like linear momentum.
Yeah.
So yeah, it's very much the same.
You know, like I could throw this staple up, and as I throw it up, I can throw the marker.
Yeah.
And then it goes boom, and then, you know,
Yeah.
something like that.
That makes sense.
Yeah.
So the 10 with the 0.2 squared, that's due to the shift of the center of mass, right?
Yeah, this is the moment of inertia shift of the bat from here to here.
And then what's the other one?
This one, this is the moment of inertia of the ball with respect to the new center of mass.
Hmm.
Then that's omega final. Now we calculate the original angular momentum of the system with respect to the new center of mass. Well, originally the bat is not spinning, so only the ball has angular momentum, right? So what is the angular momentum of the ball? About that new center of mass. So it's going to be R crossed into P. See how the angle is not 90?
Mm.
R crossed into P. This is the new center of mass, R
Mhm.
crossed into P.
Mhm.
It's out of the board. So when this guy hits this one, they're going to start spinning this way. Oh, you know what? I wrote this wrong. They're not going to spin this way. They're going to actually spin this way.
Yeah. Well, because when you first drew it, you had it hitting it above the center of mass. And
Oh,
then
yeah,
you
yeah, yeah. I
changed
did it below, yeah.
I had to erase.
So it's going to go like that, yeah.
Yeah.
So R crossed into P is what? Well, you don't know the distance from here to
Right.
here, right? R, P, sine of the angle theta, right?
Mhm.
But then what happens is R sine theta doesn't change.
Yeah.
R sine theta is just that little piece, right? Because this is R, it's
Yeah.
like this, and you're going this way, right? So R sine theta is like just this. This is R, this is theta. R sine theta is just that little piece.
Okay. Because the triangle would just keep getting smaller, isn't it?
Yeah, the triangle is getting smaller.
Yeah, so it
As,
doesn't
as
really
the
matter.
object is getting like this, R is getting smaller, P is remaining the same,
Yeah,
theta is getting larger.
so
Right.
it doesn't matter the distance.
Yeah, this could be a good thing, like a bullet
Mm-hmm.
going, hitting a dinosaur. Right? So where's the center of mass of the dinosaur?
Is it that?
R crossed into P,
Look at that hat.
right?
Oh yeah.
So then what's gonna happen? Phew, they're gonna rotate this way, right? But if the bullet is going right at the heart or right at the center of mass, then R is that way and P is this way. So there's no rotation. It just goes and hits it. So I don't know if you're a hunter, do you want to give torque on an animal when you shoot it, when you kill it?
Usually you hit, well, it's funny, we call it center mass too. We always hit center mass.
Do you go hunting?
I used to when I was younger.
Yeah.
But you go center mass because that's where the most concentration
Usually
of
the
the
heart
organs.
is, the organs.
And it's a bigger target for you not to miss. So if
Yeah.
you aim for the head, there's a much better chance you're gonna miss. But you aim for what we call center mass. Even if you go to like
Oh, so
the-
basically you aim here because the organs are there, but you don't give a torque, much of a torque.
Yeah.
It just dies.
even if you go to like the shooting range and the targets, they actually use that phrase center mass. You want to shoot right at the
Yeah.
center of the target. You have a better chance of hitting it.
Yeah, but if for physics sake,
Yeah.
I would aim for the head to give the most torque,
Well,
right? So that I want
Well,
to see that neck snapping.
if you go up to like, if you go up to Burrow Canyon, they have a lot of targets that would be perfect for. Actually, there's a lot of physics. There's nothing but physics
Yeah.
in shooting, but they have two like metal disc with a little post in the middle that's on a pivot. So when you shoot it, it spins around.
Oh yeah,
So it's exactly what you're saying. But if you were to shoot it lower, it would just
exactly.
rock back
It would
and
just
forth.
rock back and forth.
Yeah.
Yeah, perfect. Yep. So that's the angular momentum that you're giving it is with respect to the final center of mass. So then what do you need? You just need that little difference, NBH. We call that NBH. That's the original that's the original angular momentum of their system. So then M is the mass of the ball. The velocity is the velocity it's coming in at, 3. Right? And then 2, 3. And then the H is what? The difference between where it's coming and that final center of mass, which is 1 meter.
Yeah, the new center mass, not the old one. Okay.
There you go. You can now solve for omega final. 2 times 3 times divided by all that. Then I'm going to change this to a elastic collision, and I'll do a baseball example. The guy is swinging the baseball bat, and the ball is coming, hitting the tip of the bat, but then it's not getting stuck to it. Nice. Nice baseball example. Okay, so it's going to be just 6 divided by all of this, right? What you want to do in an example like this, you want to calculate the final moment of inertia because you might need that. Because the question could say, find the percent loss of energy, right? So in order to do that, you're going to need the moment of inertia of the system anyway. So let's calculate the moment of inertia. 4.2666 plus 10 times 0.2 squared plus 2. So this moment of inertia is 6.666. Uh-oh, the unlucky number is 6. So omega final is going to be 6 divided by that. 6 divided by 6.666. 0.9 radians per second. So that's the rate at which this thing is rotating. 0.9 rads per second. Okay, how do I find the final V center of mass? So once it gets stuck to it, not only is the system gonna rotate, but it's gonna move.
Oh, yeah.
Yeah, we still didn't do that. So
I forgot we're in
what
outer
kind of
space.
conservation law do we have to use for that?
Rotational kinetic.
No, it's translation.
Yeah.
It's linear momentum conservation.
Oh, yeah.
Yeah, linear momentum conservation. It's like if the staple were to go up in there and I hit it, it hits the momentum of the ball, translates into the momentum of the ball staple system, both angular and linear, right? So what's the original linear momentum of the ball? 2 times 3. And you don't have to worry about where it's hitting the bat. It doesn't matter. Linear momentum only cares about mass times velocity.
Right.
You see? So linear momentum of the ball, P initial is P final, so 2 times 3. What's the final momentum of the system? The ball becomes part of the bat. So what's the total mass?
Mass 1 plus
12 kilograms, right?
Okay.
Times the V center of mass of the system. That's it. It's just like a problem, like a block goes, hits another block, gets stuck to it. Together they move like what you're gonna have Monday, you know. But that's a piece of cake to these problems, right? So with this one, momentum is easy to do. Angular momentum tougher, you see.
Okay.
So VCM is gonna be what? 0.5 meters per second. So together they're gonna move forward 0.5 meters per second, right? And then this guy is gonna get stuck to it, and then it's also gonna spin. So it's gonna spin like this, and it's gonna move forward, you see? Now, what's the percent loss of kinetic energy? Because it's an inelastic collision, you have to lose energy, you see? So then what's gonna happen? What's the original kinetic energy of the system? Well, since this is not moving originally, only this guy is moving, right?
Mhm.
So then you're gonna have 1/2 times 2 times 3 squared. 9 joules is the original energy. Right? What's the final energy?
Include both masses.
Okay? After the collision, do you have translational energy and rotational energy, or only rotational energy?
Well, we solve for both, so I'd say both.
Yeah, exactly. If you solve for both,
You got it,
omega
yeah.
and VCM, this gives you kinetic energy of translation, kinetic energy of rotation. See? So then you have here 1/2 m VCM squared plus 1/2 I omega final squared. What's my m?
They're both masses, right?
Perfect. Because they act as a system going forward together at the same speed. You see? So that's a 12 kilogram times the velocity is a half squared. 12 kilogram half squared plus 1/2. What's the moment of inertia of the system? We wrote it here. 6.666. What's the omega final? 0.9. Now you might say, wow, it has 2 kinds of energies. They're probably going to add up to give you more than 9. Because originally you only had translational. But no, it can't add up to give you more than 9. If you did it right, you have to lose energy. Right? You cannot gain energy. So 6 times 0.5 squared. So 1.5 is this one, plus this one is 0.5 times 6.6666 plus 0.9 squared equals 4.143. Of course, when you add them, you get 5.64333. You see? So this is your clue that if you did it right or wrong. Your energy, if you got more than 9, that's you did it wrong. If you got too small, it also doesn't make sense, like 0.0 something, you know. So it should be slightly smaller than that.
You can kind of tell from the velocities too.
Yeah, exactly. So then the percent loss of energy is percent loss of energy is what? Nine minus 5.6433 over 9.
Times 100%.
37.3% loss of energy. This is kind of like reminds me of the if I'm right, there was a scene. Oh. Was there something like that similar in gravity, where they're in outer space and they're spinning, right?
I believe
I
that they're
remember
both streaming,
vaguely.
like holding each other, right?
Yeah.
Yeah. It's been a while since I've seen
Those kind of movies, of course, I'm more interested in the physics. No, I'm not.
it. Have you seen Interstellar?
Yeah, of course, yeah.
They based all the graphics off of actual modeling of black holes and what they think it might look like.
Oh, this isn't the scene I'm thinking about. There's a scene where her and Clooney are.
Like
Maybe this one.
they're rotating and let's go, right?
That's it?
Well,
So that I can.
Oh, that was just.
it was the trailer, yeah. But yeah, for Interstellar, they use like the actual modeling.
This is the best Uber. I got Wi-Fi, TV, water.
Is from a BSC stat. That's not me. I have a Dr. Stone requesting faster transport.
We have to go, we have to go.
Copy.
Explorer permission to retrieve Dr.
The
Stone.
physics of this, all the motions in space, they're all the stuff that we're talking about. All these rotations. See that? How she grabs him and they spin?
Hell out of here. No, don't wait for us. Man down. Man down.
There's so much physics going on here.
Yeah.
You see the spin? Now you gotta pause this one by one and see do a problem based on it. Right?
Listen to my voice. You need to focus. I'm losing visual.
So she became part of this.
What's the moment of inertia of that rod and him sitting?
And then the rod gets shorter when it gets
Yeah.
detached. And how much?
Okay, now you see?
Okay.
He goes like this, he starts spinning.
Around its his center.
His center of mass.
Oh.
Ah. Yeah, pick apart all those scenes. There's another one from the Mars movie.
The Martian? Or
From Martian.
oh, the one where he uses his thumb to
No, at
changes.
the end where
Like the air from his thumb to direct his flight path?
And he catches.
Yeah, that's what I was talking about. Where he flies like Iron Man.
He's rescued.
Yeah, there you go.
Something like that.
Yeah, he flies like Iron Man with the thrust from the air of his suit.
This is the best Uber. I got Wi-Fi, TV, water, my shop chairs.
You have that. Hook me up.
Oh yeah, there's a good physics in here too.
Oh,
Look.
I have visual on the map.
What's the intercept range?
I'm checking. 312 meters.
Did you say 312? Great, I'll wave at you guys as I go by.
The kick gets you, Mark. You're too far. I'm not gonna make it.
I know.
Bet I hope
See,
you
he's
can't go
spinning,
into-
so he's got angular momentum,
I got this.
right, of spin.
So that's what I was talking about. He cuts his
Oh, okay.
the air to direct his.
Okay, yeah, the air is causing him to spin even more, right?
Yeah. He's trying to use it as thrust to escape his.
Mark, report.
On my way, Commander.
Okay, now he starts coming like this, like a bullet, right?
Yeah.
And he's gonna hit her, I think.
Yeah.
There's
It's a chaotic orbit though.
5.2 meters per second.
Copy. Just in course.
Okay, now she's gonna try to catch him, right?
3.1 meters per second. Distance to target 24 meters.
Oh, he's gonna try to grab onto a rope, I think.
11 meters to target.
6 meters.
Okay, now he's not able to. But she starts spinning because at least she touched her,
That's what he
right?
gave him. Yeah. Oh, and now they're spinning around.
They're spinning together.
Ah.
Angular momentum right there, you see that?
I never saw it the same way before.
Now they're starting to wrap.
And it's just like your problem from earlier around the.
There's like 10
ice
physics
skating.
problems right
No,
there.
but it's like your ice skating one
Yeah.
because it's wrapping around.
And now she's pulling him.
I got him.
Shouldn't they rotate faster?
Yeah, there's a bit of a mistake there. They should be rotating faster, right?
Back, pull us in.
Come on, it should be zzz.
It's good to see you.
Well, they might still have some atmosphere. Because they're not that far away from. No, planet has no atmosphere. Mars has no.
They're way out above
Yeah,
Mars.
that's way,
They're way
yeah,
above
sorry.
Mars.
I forgot.
The only thing I'd rather be doing than driving.
So there's a lot of that kind of stuff.
Professionally, 14 years. If I see
But his
someone-
initial kick was only the thrust from the air, so maybe
But he was going fast.
that is
So
true.
he's going fast.
'Cause he had to
and
travel
do the
three-
rope, and then she's at the top of the bottom of the rope, and then he goes and hits her, and together they spin.
Yeah, he had to travel 312 meters in a short amount of time. So yeah, you're right.
Yeah.
He was going super fast. I had never seen it that way before.
Yeah, of course.
this-
When you study all these things,
Uh-huh.
the whole
Okay,
view everything
very
differently.
It's just the way I am.
Okay, now let's look at the baseball bat. Let's see the specifics. I'm gonna assume the bat has the same linear mass density that we already did, so we don't have to do another integral.
Yeah.
You know, so, but I just wanna get the mass of the bat. So the mass of the bat, although historical bats approaching 3 pounds, today bats are
About a
0.94. So the mass of bat is 0.94 kilogram. Mass of bat, 0.94 kilogram. And the length of the bat is what? Does it give that?
No more than 42.
42 inches?
No more than 42 inches.
Okay, I think the professionals use.
So, but look, it's
right?
about a meter.
42 inches.
So it's about a
Oh
meter.
yeah, it does tell you 1.06. So let's just say easy 1 meter.
Well, they say the bat can go up to 1 kilogram too.
Huh?
So the bats.
Okay, let's just make it easy.
Yeah, I was about
Let's
to say.
make the
1
mass
kilogram,
more,
1
that's perfect.
meter would be a lot easier to work with.
Yeah, so let's say the bat is 1 kilogram, 1 meter, and then what would that make the eye center of mass? Well, for us, the length was 4 meters, the center of mass was 3.2, right?
Mhm.
So the ratio of the center of mass to the length was, that would be 0.8. So then, in our case, the center of mass would be 0.8
Mhm.
centimeters from the end, right? So now let's say the baseball is coming, and usually does it hit the tip of the bat?
No.
Where does it usually hit?
Center of mass, right? Or where?
Where's a good place to hit it when you're trying to hit?
I thought it was the center of mass.
Is that like here?
Yeah,
Well, let's actually Google it.
that's a good
Oh, I'm saying Google.
idea. Here I am with
Optimum place to hit baseball on the bat. Sweet spot.
Yeah.
I'm thinking of the sports science that show on ESPN.
Mhm.
They go a lot, these kinds of things. Look, because of the location the ball struck the bat, in our development of the speed bat, we discovered the optimum location for the ball to hit the bat is 17 to 21 inches from the player's top hand.
Ah,
Uh,
because it's
this
not
is the location of
rotating
the bat
around
that
it.
results in the most powerful hits every single time.
Because it doesn't depend on the length of the bat, but the length of the bat plus the length of the arm of the swinger, right? Because it's pivoting around the center mass.
So if you're holding it like this from the what hand you say it's? From the top hand, 17 to 21 inches.
Yeah. So it's not just it's not.
So if your top hand is like that, so where's the pivot point there?
What the
In
pivot
that
point is
case?
actually in the person.
Oh, yeah, yeah.
That's
yeah,
what I was
yeah,
saying.
yeah,
Like it
yeah.
doesn't depend just on the bat because the bat's not rotating itself. It's on the person, and that's why it depends on the length of the arm.
Oh, yeah, that is true.
Yeah.
So you're not rotating it like
That's
that.
why they said it's from the top hand because that's variable, and that's why there's like a range too. Probably because of depending on how long a person's arm is probably going to be somewhere from 17 to 21.
Yeah, so how many, change that to meters, let's see.
We could like figure out what the average length of an arm is, and yeah, because it would be because the more concentrated mass would be further away. from the
43
pivot point.
centimeters.
This would be the center of the
So
person.
about
and
50
the bat's heavier.
centimeters.
Yeah.
17 to 21 inches is about 50 centimeters. So that would be 50 centimeters from the top hand would be right here, right? Top hand, you're holding it from there.
Yeah, he has a point. Like, what
Huh?
happens if Shaq hits the baseball? Wouldn't, like, since his arms are so long, it'd be like a
Yeah.
lot more powerful. That'd be
The
interesting.
Shaq of baseball is, what's his name? The Boston Red Sox, that big guy, Big Papa.
I guess that's why there's
Is
usually.
he retired?
I guess that's why baseball players are usually fairly tall
Yeah.
and lean, so they can. That's good.
So yellow.
So the more
all that
concentration of
contact,
mass is
blue line, the bat.
Because if they're heavier, they can't. The moment of inertia of the person is going to be bigger, but if they're lighter, it's going to be less. So the bat can actually get more velocity. That's
Oh,
kinda
they actually give you all the stuff in this picture.
Well, because it's going to be harder to rotate yourself. So if you're lighter, but you have longer arms, you'll be able to get the bat going a lot faster.
Okay, yellow
They
circle,
have to be tall.
the ball at the
Yeah.
contact. Blue line, the bat, 34 inches. Red line, the distance from top of hand to there. So essentially,
Not there.
yellow circle is where the ball, so 17.4 inches. So it looks like it's kind of close to the center of mass of
Yeah.
of the bat, right? Huh?
Yeah. I'd say we could just use that for this example.
Okay, yeah, just why don't we just use that at the, so, you're
'Cause I
saying
mean-
the best place is right there.
Yeah, it
So
depends
let's
on-
say the ball is coming at 90 miles an hour, or these days, pitchers are always pitching at 100 miles an hour.
Yeah.
Remember when the 90 was so
Yeah.
rare? Now it's like 100. Okay, how many meters per second is that? Oh, back to chapter 1, right? Conversion of
Okay.
units. 1600, 3600, 100. What was the conversion? 1600 meters is, so this is miles per hour, right?
I could do that by hand.
So
5,000.
1 mile is 1600 meters, 1 hour, 3600 seconds.
Okay.
Okay, so then you're gonna have 100 times 4 ninths. So basically, it ends up being the ratio of 4 ninths. So the original speed is around 45 meters per second. Okay, comes and hits the center of mass, right? And then your distance from there to the pivot point is what? Because it's pivoting around your body, right?
Mm-hmm.
So what's the distance from the edge of the bat to here, to the center of your body? Estimate from here, bat, to the edge. So that's another half a meter probably, right? So let's mimic this as a perfectly elastic collision, right? But I also have to give the original swing speed, because in that case, you're originally swinging, you're not holding the bat like
Yeah.
this unless you're bunting, you know? So what's a typical swing speed? Let's look that up. Researching the average bat speed of an MLB player, you quickly find a multitude of single answers, between 70 to 80 miles an hour.
You take the average,
Yeah.
75 miles per hour. Or you just take that number.
Or take a certain number that gives us a whole number. So if we do that times 4 ninths, ratio of 4 ninths, right? So that means your swing speed is a little slower than the ball speed, right?
But yeah, a lot more
So
than that.
70, let's say,
Moment, gravitational velocity, translation.
okay, around 30 meters per second. Oh wait, is that at the tip of is that the tangential speed at the tip, or what do they mean? You see, if they give us the answer in radians per second, we can say, okay, that's the angular velocity of the baseball bat. But if they give you in meters or miles per hour, then you have to ask yourself, what's the speed? Is that the speed of the tip, right?
Yeah.
Or is that the speed at your hand?
I would assume they would use the tip. Like, I can't imagine they have a device to be able to measure the hands and not accidentally
Yeah, I think it's
test.
probably the tip. So
Yeah.
they're saying the speed at the tip is 30 meters, what did I say, 30? Yeah, around 30 meters per second. Did we already say the mass of the bat?
One kilogram.
Did we say the mass of the ball?
No.
Okay, then that's the last thing to do. Mass of the baseball bat.
Well, oh yeah, you're right. Mass of baseball.
Baseball.
In
No,
kil-
just the baseball
Yeah,
itself.
in kilograms, so.
About 0.15 kilograms. Okay, model this as perfectly elastic. Tell me the final velocity of the ball when the ball bounces back from the bat.
Is it perfectly elastic?
Yeah, I'm modeling it as perfectly elastic collision. So find the velocity of the ball as it's bouncing back. V final, and find the final velocity of the center of mass of the bat, VCM, and the final omega of the bat. So there's three unknowns in a perfectly elastic collision. I have to conserve what? Linear momentum, angular momentum, and kinetic energy.
Yeah,
All three. Right? So linear momentum is the easiest conservation, right? P initial equals P final. What's the P initial? This guy is going to the left, right? Or to the right, and this guy is going to the left. You know what? Let's assume 30 meters per second. It's going to make it easier. Let's assume that it was the speed at the center of mass. Because if it's the speed at the tip, we have to do more work. I'm feeling lazy.
Yeah, you're right.
Okay.
And it might
You
be
know what
too.
I mean? And it might have been anyway, you know.
Yeah.
So the center of mass of the bat is going 30. Okay, so then that's easier. So now that makes it 0.15 is the mass of the ball, right? Times the speed of the ball is 45 minus this guy, right? Which is going to be 1 kilogram times 30. So is the original momentum negative or positive?
Which way do you say that?
Yeah, I guess which way are you saying? We could make this positive. Yeah, you know what? Let's make this direction positive. I think it's better.
Yeah, because that's where we want it.
Yeah, we were kind of interested in that direction more. So we can make this guy the positive, 1 times 30, and then make this guy the negative. So let's see, 0.15 times 45, 10. Oh, it looks like it's going to be positive, yeah. Yeah. So that means the final momentum is going to be this way, right? So this direction is positive. So then that's going to equal to the final momentum, which is what? 0.15 V final plus the mass of the bat, 1 times what? VCM. There it is. So this minus this.
Oh, you made that one back.
$23.25. 0.15 V final plus VCM. That's linear momentum conservation. Now let's do angular momentum conservation. What's the original angular momentum of the ball? Okay, around which point is this thing rotating? Oh, it's around
The person.
this guy, right?
So, yeah.
Oh, okay. So
So
here's where we have to be
0.5.
careful. Angular momentum, you have to really put your thinking hats on. So around which point it's rotating? Around here, right?
Mhm.
So then the original angular momentum of this guy is positive, right?
Mhm.
Since we're considering this a positive direction. That one is negative, right?
Right.
So then the distance here is gonna be what? R crossing to P, so then this distance is what matters,
Oh.
right? So then for the bat, we're gonna do what? I initial of the bat, omega initial, minus the ball, M ball, V ball, H ball is equal to, then at the end you're gonna have M ball, V ball, H ball, plus I final, omega final. So let's put in the numbers. What's the I initial of the bat? Well, the bat is not rotated around the end, it's rotated around the point of the center. So what do? Parallel axis theorem. So what's the moment of inertia of my bat? What was the moment of inertia of my bat?
0.8 meters.
No, but the moment of inertia.
Oh,
Remember it was 4.666.
Yeah, or was
But
it
that was when it was
4.2?
10 kilograms and 4 meters, right?
Right.
ICM.
And it was 4.266.
Oh, 4 point what?
266.
266?
Yeah.
The mass was 10 kilograms and the length was 4 meters.
4 meters.
So remember, I'm using the same linear mass density so that I won't have to do it again. But now the mass is changed to 1 kilogram, 1 meter. So how is this moment of inertia gonna change ICM?
You shift it to.
No, I'm not shifting it. I'm just saying, if I change the mass to 1 and the length to 1, how does that change this guy?
Well, linear mass density, so...
No, just changing the mass.
Okay, so we got mass over length.
Or is there no easy way to do it?
But didn't you just do something like that before, where you got a ratio of mass over length? I thought you just did something like that in the last problem to convert it over. I don't think I wrote that part down.
Length. Is there an easy way to change it? Because that was the moment of inertia around the center of mass when it was a 4 meter bat and a 10 kilogram bat. So I'm just trying to see if there's a quick way we can do. What if it's a 1 kilogram bat?
I feel like you change the limits.
Yeah.
Do we have to do all over again?
You change the
Do I have to do the integral all over again?
Yeah, you have to do that.
Yeah.
So what would I have to do? How do you find the moment of inertia? I've forgotten.
But you're gonna.
It's the final, I've forgotten. Give me help. I'm panicking.
You're gonna like set origin. Which point is the origin?
This one. Because the point that determines the origin is the point where the alpha is measured from. Alpha, lambda of x is alpha x, what was it, cubed?
Alpha x cubed.
Was it cubed?
Yes.
So where was the x measured from? From the left end of the bat, right?
Yeah.
So then that's where you measure from.
Right.
So pi is x squared dm, dm is lambda dx, then you do your x squared lambda is alpha x cubed dx, 0 to L. That's why it's good to sometimes get a general answer.
Yeah.
That way you're not stuck to the 4.266, right?
Yeah.
So you can just say alpha integral 0 to L, x to the 5 dx, alpha L to the 6 over 6, right? Is that right? X squared,
Yeah.
x cubed, alpha. But then you do another integral for the m.
Yeah.
Integral lambda dx, alpha x cubed dx, 0 to L, m is equal to alpha L to the 4th over 4, alpha is equal to 4m over L to the 4th.
You take that.
Then take that, put it into there, I is equal to 4m over L to the 4th times L to the 6th over 6, 2/3 mL squared. Then you shift that to the center of mass, right? Then what was the center of mass of that thing? Then you do another integral for the center of mass. Integral alpha x cubed times x dx over integral
center of mass
alpha x
from the
cubed
equation?
dx. Huh?
Didn't we know the center of mass in this equation?
Well, I'm trying to do a general
Okay,
thing
yeah.
so that then
Yeah.
I can just,
Okay.
so then the alpha cancel, then you get your x to the 4th dx over integral x cubed dx, 0 to L, 0 to L, L to the 5th over 5 over L to the 4th over 4. Oh, and then that's 80%, yeah, exactly. We get a ratio of 4/5 L. That's why it's 80% of the length,
Yeah,
right,
that's
exactly,
it.
yeah. Right, then you shift this down by 80% of the length, right? I center of mass, 2/3 mL squared minus m 4/5 L squared. Oof, right? All of that to say 2/3 ml squared minus 16/25 ml squared. Then cross multiply 50 minus 48. 2/75 ml squared. Okay, now I can put that in here with our mass and our length. And then that'll be the I center of mass. So 2/75, the mass is 1 kilogram and the length of the ball is 1. 1 times 1 squared. So 2/75. Oh, but then the ball is not, the bat is not, that's ICM of the bat.
Yeah.
Then I can shift it all the way down to the center of mass of the player. That'll give you the total moment of inertia. So this is ICM, right? Then the I is going to be what? Wow. Ooh. This will end today, and then Wednesday we'll continue this great problem. Awesome problem.
Excellent.
Plus m times,
D squared.
the distance is 0.8 plus 0.5, 1.3.
That's H, right?
That would be your same thing as we're using for the H, right? Where did we put it?
Right there.
Well, so far we've got this equation. We're trying to develop the angular momentum equation. Okay, so then let's just stop at that point. Let's calculate the moment of inertia. Then we're going to use that several times. $1.717. Okay, so then let's continue that Wednesday. Whew, good problem, huh? I like it when we apply it to real life situations too, like that. Baseball.